Jai Hind, my dear students. Today we are going to start a topic within the control unit hardware, that is instruction cycle. We know that control unit hardware is a part of control unit. So let's proceed. I am Dr. Akhilesh Verma, professor in Department of Computer Science and Engineering, and we are going to understand what is a microoperation. So as name evident, and you have some idea that micro means small. So a microoperation is a very simple and very little step in computer machine. Okay, so the most simple step, and that is doing a very little task, that is called as microoperations. Now, when we consider a program that we write for a computer, so we say that the program is a sequence of execution of instructions. So I1 is followed by I2 is followed by I3 and so on, and that is called as program. So each instruction has multiple stages, and these stages are called as fetch, decode, okay, then interrupt and execute, etc. So whenever each of these involves in execution of an instruction, they are basically broken into more smaller part. So fetch is broken into microoperation 1, microoperation 2, microoperation 3, and so on. So a instruction is executed by multiple microoperations, and it has a nature that it is a smallest or atomic operation, and that cannot be divided further. And that's why we can say that this approach is called as function decomposition approach. So program is divided into instructions, okay, and instruction is further divided into microoperations and so on. So we are dividing a program as a function into multiple instruction, and then a particular instruction is divided into multiple microoperations. So in this diagram we can easily see and understand the purpose of microoperation, to divide a functional block, that is the program, into multiple instructions I1, I2, I, and each instruction is further decomposed into a group of microoperation named fetch, indirect, execute, and interrupt. So it is basically a functional part or atomic operation of a processor. That is what exactly being functioning within the CPU is called microoperation. So it is a functional step and the smallest step of a given computer machine. A single microoperation generally involves transfer between registers. So this is first category, that is register to register transfer operation, and it also involve transfer between register to external bus. So we can say the second category is from register to bus, and the third category is all the ALU operations, that is the execution part that happens within the CPU. Okay, so microoperations are generally classified into three sets of three class of operations: register to register transfer, and register to bus transfer, and all the ALU operations that takes turn. So if we see that this functional division, we can think about making a sandwich as a one program. So, the program execution, it is overall goal like make a peanut butter and a jelly sandwich. Okay. So, it is broken into machine instruction. So, we break that high level steps into recipe like get bread, spread peanut butter, then spread jelly, put slice together. Okay. Now, if we see these high level instruction are broken into machine instruction, they are not the basic one. They are further divided into smaller ones that are called as micro operation. So, let's have an example like uh, uh, we have to perform a particular task like for getting the bread. So, we have to open the cupboard, one micro operation, then grab the bread bag, that is second micro operation, then untwist and tie the bag, then take out one slice, place the slide on the plate. So, we can see with the real world example how a computer program is executed at the smallest level, that is called as micro operation, starting from the program execution to the machine instruction to the finally to the micro operations. Fine. Okay, let's proceed to understand more in detail that how we can see these transformation from higher level to the lower level. So, we can see that the machine instruction like add, okay, number from memory to a register is translated by processor control unit into microprogram. So, one micro instruction is converted into microprogram, okay, which is a nothing but it is a simply a which is a simply which is simply a which is a simply a uh, sequence of micro instructions that are operated or also called as micro operations that processor execute one by one. Okay. Now, if we see the state wise or step wise, so we can see that a micro operation is physically executed for each step or state in a processor timing cycle that we will discuss later part is driven by a clock. So, one micro instruction is uh, performed at one cycle, or it is represented as control word, a set of binary bits that tells different hardware components like ALU register exactly what to do at which particular clock. Fine. So, this is steps are broken into states and the states are broken into micro instruction, and the micro instruction is nothing but is a group of control word that execute a particular higher level task. Okay. Now, if we see this pictorial diagram of the multiple blocks within the CPU, we are earlier familiar with the CPU has multiple register like program counter, memory address register, control unit, memory buffer register, and it is also called as MDR in the various books. So, that is why I have used the board notation MBR in the diagram, and we are using MDR in the text here. Okay, and if you see these are connected through internal bus system, and also this CPU is connected to outside buses, address data bus, and finally it is connected to memory. So, MBR means memory buffer register, that is called as MDR also. Some books MAR is called memory address register, it is called MAR in some other books. Okay, IR is instruction register that is containing the instruction, and PC is the program counter that takes the sequence which particular instruction to be executed. So, what happens at each clock pulse, okay, time unit which are equal in duration, that is shown here. Okay, each clock pulse defines the time unit which are equal in duration. So, we can see here this is equal in duration, this is one clock pulse, then this is another clock pulse, and so on, this is clock pulse. Okay. So, each clock pulse defines a time unit which are equal in duration. Micro operations are performed within this time unit. Okay. So, one micro operation is performed within this time unit. So, this is the control time. if multiple micro operations do not interfere with each one another, means there is no conflict in the micro operations, that is the transfer of data that does not interfere with each other. Okay, so we can perform a grouping of micro operations and within one unit. So, like example, the grouping can be performed as long as there is a proper sequence of event are followed. Like program counter data is sent to the MAR must be done first in order to perform the next step, memory to MBR data operation, because program counter will send the memory address data to MAR, and then memory will operate and find that data and send that data to MAR or MDR. Okay. Similarly, we can conflict, we have to put in a sequence, and finally, if they have conflicts, so if we are sending memory data to MDR, okay, cannot be at the same time that MDR data is sent to IR, because both are conflicting with each other. Okay, so this is how the micro operations are visualized within the hardware of a computer. Okay, so this particular diagram you can see here that there is a transfer of data that happens from CPU to bus or memory, and that is performed by the micro operation. So we can easily see that three class of operation, register to register and register to bus, and within the CPU, that is execution operation. Now come to the CPU clock. Now what is CPU clock? It is a repetitive sequence of pulses. We can see these pulses. Okay, it is useful for measuring the duration of micro operation. So why it is used? It is used to refer the time duration for which the micro operation will execute, and must be long enough to allow the signal to go. Now this clock or the pulse should be long enough that in that period particular micro operations is complete, because there is a transfer of data from one point to another point. So signal is transferred. Okay, so different control signals at different time within this instruction cycles are executed by using this CPU clocks. Need a counter with the different control signals for T1, T2 and T3. So now a additional circuit that is called as counter is needed to count these clocks. Okay, additional circuit is needed apart from the clock. So it will identify a particular clock has passed, like T1 has passed or T2 has passed, etc. Now see it further. Okay, here we can see. Okay, this clock act as a timer. Okay, okay. So it act as a timer. Okay. Now if we see, it drives a sequence of which generates the timing signal through T0 to T4. So what is the purpose of this clock? It to generate timing signals from T0 to T4, one after another. These timing signals are used to turn on other parts of circuit. Okay, this is very important. So T1 will turn something, T2 will turn something, and so on. And there is a clear sequence counter instruction at the end, which we can see here that at T end of T3, okay, when it gets 1, okay, the clock, the T0 starts again. Okay, so T0, T1, T2 and T4, after T4 has passed, the clock will start at T0 again. Okay, now let's understand one by one the various cycles within the instruction. Okay, now we have to remember this diagram every moment, so we can draw it side by side to understand the each cycle. So what is fetch cycle? The purpose of fetch cycle is to get the instruction from the memory to the instruction register IR. Okay, so certainly at the beginning of instruction the program counter is there. So at time T1 the data of program counter, the program counter will tell the which memory location we have to fetch the instruction. Okay, now as time T1 has passed, okay, so from PC the content has gone to MAR. Okay, now as T1 has passed, okay, what will happen? The data, the memory knows the address, so it will send the data from memory to the MDR. Okay, so next cycle the data will be copied back to the MBR or MDR. Fine. Now, since we have already fetched the content of program counter PC to the MDR, now it is necessary to update the PC value to the next instruction. So, PC is updated to PC plus 1 and the PC is now updated with the new instruction to be fetched in the next cycle. Now, we already know that MDR contains the instruction. So, we will copy the instruction to the instruction register IR. So, it will go to IR. Fine. So, this is how the fetch cycle takes the instruction from the memory to the IR. Now, we have fetched, okay, now there is possibility that we need to fetch other datas that are not directly in the instruction. Okay, so it occurs when there is an indirect address. Okay, so it consists of 3 time unit and 3 micro operations. So what are this? The data is transferred to MAR from the IR. So the instruction register has certain flags that indicates it is an indirect operation. Okay, so what will happen? The IR will send the address part or the indirect address calculation part to the MAR. Okay, so the MAR IR will send the MAR. Okay, and then the memory will know from where this indirect address is to be brought. So that particular address data is brought to the MDR. Okay, so the data again go to the MDR and the content of MDR is now updated in IR, particularly for the address part, not for the operation part. Okay, so operand is updated. Okay, so it was earlier indirect, so it is now become direct. Fine. So this will consume 3 cycles. Now all must know there might be more than 2 indirect operations. Okay, so when there is an indirect cycle for first indirect operation, okay, this will repeat. Okay, these 3 steps will repeat first time, and the for second indirect operation, okay, this will repeat again. So there will be fetch of the data, okay, that is operand part from the main memory indirectly through these steps. Okay, now we have got data. We have earlier fetched the instruction part, then instruction is decoded, and instruction is decoded by control unit, and we came to know about the whether is it directly available data is there or indirect data is available there. So this is first cycle will be followed by indirect cycle. We bring data to the instruction register by indirect cycle. Now interrupt cycle is to be understand before the execution cycle. That is needed for one reason, that there are chances that when interrupt is enabled, then interrupt has to be handled. Okay, so it happens after execution cycle, that is this one. Okay, but we are understanding the interrupt cycle for the reason that we have to take care of the enable signal of the interrupt. Okay, so when there is enabled signal, then the control unit will recognize that there is an interrupt. Okay, so what will happen? Certainly, if we have finished the execution cycle, the contents of PC are transferred to MDR so that they can be saved to return from the interrupt. So at T1, when interrupt has after execution, the current PC is sent to MDR. What is the reason? That we have to save it for the future reference because we have been interrupted. Okay, so what will happen? Then MAR is loaded with the address at which the contents of PC are to be saved. Now we have sent the PC part to MDR, and also we will send a address that where this PC part will be sent. So the MAR is updated with the saved address where we have to save it. Okay, now after that there will be we have to bring the routine address, that is the uh, interrupt signal will tell which particular routine is to be executed when the execution, after execution, that we have to start the interrupt cycle. Okay, then the PC is now updated with the routine address, that is the interrupt driven interrupt service routine. Okay, now we already have that particular old PC to the MDR, and we have also sent the location where we have to save it. Now the MDR content is updated in the main memory. So now at this stage, the old PC, that is from where we have been interrupted, is saved. Okay, so now understand the execution cycle. The execution cycle is not predictable as other cycle, fetch, indirect or interrupt. Reason being that how much time it will take vary depend upon the execution cycle. Okay, so for example, in the following cycle, we can see that add R1X means that the data of memory location X, okay, is added with R1 and saved at R1. So what will happen? First, the IR instruction register, this one IR has some location for X. Okay, so the X will be get transferred to the MAR location. Okay, so now the memory knows the from which location we have to bring the data. So X is known to the memory. So the data from X location, okay, X location is copied to the MDR. Now MDR contains the data. So MDR contains the data. Okay, so we have already register available in the CPU, and MDR has the data from the location X. So MDR is added with R1 and it is sent to the location R. Fine. So this is very simple thing, that how the CPU executes at the click of the clock cycles. Okay, fetch cycle, indirect cycle, interrupt cycle, and execute cycle. So how this is managed? Okay, so to manage this, there are 2 bits register within the control unit. Okay, and by that 2 bits there are 4 possibilities that is shown here, and instruction cycle code is stored there, and it designates which part of the cycle the processor is in. Okay, so each phase is decomposed into sequence of elementary microoperation, fetch, indirect, and so on. So when we execute cycle, one sequence of microoperation for each opcode will execute, and it need to tie a sequence of microoperation together. Okay, that we have already discussed. And for the next set of micro instruction cycle that has to be executed, depends upon the 2-bit register in the instruction cycle code. Okay, so we can see here with the flow chart that what ICC is. Whatever the value of ICC is, okay, like it is 00, then it will move to the fetch part. Okay, so fetch cycle will execute the fetch instruction. Okay, and certainly if there is a fetch, there might be possibility of indirect operation. Okay, so if there is an indirect operation, so it will say yes, then it will be set to indirect, that is this is 1 okay, sorry, this is 1 okay, yes, so it will go back to this point and then go here. Okay, if it is no indirect operation, then it will directly go, okay, 10 means execute, so it will directly go to execute. Fine, so we can see here from the ICC register value, the flow chart of instruction clearly indicates how we can switch between the various state while we are executing the instruction. Fine. So dear students, before we finish, we can think in the backward slice movement, how the instructions are executed through micro operation. So this is a flow chart that shows how various micro operations are clubbed together within the control unit through ICC. Okay, so we can see that these ICC has the 2 bits and that can control the various cycles, and we have seen all the cycles with respect to the time T1, T2 and T3, execute cycle, interrupt cycle, indirect cycle, and the fetch cycle. And we also told that these cycles are executed at the clock, and the clock is basically a drive sequence that is given to a counter that counts the timing from T0 to T4, and there is a clear sequence counter element that reduce the count to 0 when it reaches to T4. And this is we already know that CPU is run by the CPU clock, and we can see that these micro operations are visualized in this diagram through the three sets of operations that we have discussed earlier: register to register, register to bus, and ALU operations, etc. And finally, we can see that what is the micro operation. The micro operation is very simple and accomplishes very little. So Jai Hind, dear students, for listening this important topic, and I hope you understand.